Let's apply the ratio and or root test to evaluate some series. We may find that it's inconclusive, but it's worth a shot to try. Our first series here, n squared plus 7 over n factorial. A lot of times when you see factorials, the ratio test is a good one to start out with. The reason being is because factorials have that nice cancellation property when you look at n plus 1 over n. So in this particular case, a sub n is n squared plus 7 over n factorial, as we might expect. What about a sub n plus 1? Well, that's n plus 1 squared plus 7 over n plus 1 factorial. Now, one thing to note here is that because of the way the factorial function works, n plus 1 factorial can be written as n plus 1 times n factorial. And that's going to be really key because that's going to lead to some good cancellation. So when I do the absolute value of a sub n plus 1 divided by a sub n. Now we're going to take the limit here, but I find it helpful when solving these problems to just look at the ratio first and simplify it and then apply the limit. Mathematically it's all the same, you're doing some preliminary work here and you're not having to write limit at each step, really crowding up your space. So if I do a sub n plus 1 divided by a sub n, I get n plus 1 squared plus 7 over n plus 1 n factorial all over n squared plus 7 over n factorial. Now that's pretty ugly, right? So what we do is we do the good old-fashioned tried and true multiply by the reciprocal here. So we get, I'm going to run out of space here, but you get n plus 1 squared plus 7 over n plus 1 n factorial times n factorial for n squared plus 7. So what we're going to find here is that the n factorials cancel. So we end up with, so I'm also going to, so these will cancel here, but I'm also going to go ahead and multiply this out. This will get me n squared plus 2n plus 8 over, now I have n plus 1 times n squared plus 7 gets me n cubed plus n squared plus 7n plus 7. So that's this ratio. Now if I take the limit as n goes to infinity, I hope you see that that's 0. And if you don't, I implore you to go revisit some other videos that we have about how to take limits there and using L'Hopital's rule, or not even necessarily having to for this one. But that limit's going to be 0. So by the ratio test, as long as that limit is less than 1, this is not only convergent, it's actually absolutely convergent. But that's a convergence series. Now over here we have n minus 1 factorial over 5 to the n. So in this particular case, I'm still going to use the ratio test. I could try the root test, and in fact the root test is something I would think about because I have something to the nth power. So when you have something to the nth power, the root test is a good idea. The problem is that that factorial won't play nicely with it. So generally speaking, when you see a factorial, try the ratio test. But again, these are always suggestions. They're not hard and fast rules. So again, we have a sub n is n minus 1 factorial over 5 to the n. A sub n plus 1 is n factorial 5 to the n plus 1. Now that's because, right, when we add 1, so n plus 1 minus 1, they're going to get cancellation. And then this. Now I'm going to rewrite this as n factorial over 5 times 5 to the n. Right? Because that's 5 to the 1, and by the rules of exponents we can combine those or split them apart. The reason I want to split them apart is now I have a 5 to the n that matches this. I'm actually also going to write this as n times n minus 1 factorial. So why am I doing this? I'm doing this because it's going to make our lives a lot easier when we have to divide those things. So if I'm now considering a sub n plus 1 divided by a sub n, I get n minus 1 factorial 5 to the n over n minus 1 factorial over 5 to the n. At which point I can multiply by the reciprocal of the denominator. So n minus 1 factorial 5 times 5 to the n times 5 to the n minus 1 factorial. So we're going to get 5 to the n's are going to cancel and n minus 1 factorials are going to cancel, leaving us n over 5. So if we take the limit as n goes to infinity of that, we're going to get infinity. Clearly infinity is larger than 1. That tells me that this series is divergent. So quickly I do want to talk about something here. There's this idea of order of growth. So if you studied computer science, they have this thing like big O notation, right? And big O notation talks about how certain quantities grow more quickly than other quantities. And you study things like power functions and factorials, my goodness. Factorials and polynomials and all this, and you kind of rank them about how quickly they grow. This is important because if we were going to do something like that, if we had that tool in our kit, if we knew a little more about that, if you know about order of growth, it would tell you automatically that by the nth term test, this thing's going to diverge. Because factorials grow way, way more quickly than power functions. The reason being is like, at each time step, or each index step, this thing's being multiplied by 5. But on top, when your index gets to be like 1,000 or 100,000 or something like that, that factorial is not being multiplied by 5 anymore. It's being multiplied by 5, 100,000, a million, right? And so it's just blowing it out. So the limit as n goes to infinity here, this is going to hit infinity way before that does. So I say that because the nth term test for divergence would have gotten us here without having to apply any one of these tests.